Okay, let's dive into this. Welcome back, everyone. Now, in our previous explainers, we spent a good chunk of time learning how to actually spot a function and understand its basic properties. But to solve real, tangible problems, we're going to need something more. We need a model. So today, we're opening up James Stewart's catalog of essential functions. You can really think of these as your fundamental building blocks, the absolute essential tools you're going to need in your mathematical toolbox for everything we do in calculus moving forward.
Here's a quick look at how we're organizing our toolbox today. First, why mathematical modeling? Second, linear and polynomial models. Third, power versus exponential functions. Fourth, trigonometric and transcendental. And finally, number 5, your tool matching challenge.
All right, let's kick things off with section 1. Why mathematical modeling?
Before we even jump into the equations, we have to ask, why do we even need to model real-world phenomena in the first place? Well, a mathematical model is basically a translation. It's a mathematical description of a real-world phenomenon using functions. Now look, a model is never a perfectly flawless representation of reality, mostly because Mother Nature is always a bit messier than our math. But instead, a model simplifies reality just enough to allow us to calculate things while staying accurate enough to give us really valuable predictions. Whether it's a ball falling from a building, a bacterial colony exploding in size under a microscope, or the sine wave of a sound signal bouncing around a room, functions are the primary tools we use to understand that behavior.
Moving right along to section 2, linear and polynomial models.
Let's start stocking our toolbox with the most common models out there. First up, the linear model. Y equals f of x equals mx plus b. The graph of this function is always a perfectly straight line, elegantly capturing constant change. Now what's really interesting about this slide is the m. That m is the slope, representing the exact rate of change of y with respect to x. Meanwhile, the b is your y-intercept, which is really just a fancy way of saying, hey, where does my measurement start when x is 0?
Let's pull this out of the abstract and put it into the real world. Imagine you're climbing a mountain. As you climb higher, the dry air expands and cools down. So the air temperature, which we'll call T, drops linearly as your height, h, increases. If we were to model this, the slope, m, is going to be a negative number simply because the temperature is falling. It tells you exactly how many degrees you lose for every single kilometer you climb. And that b, that's simply the starting ground temperature right before you took your very first step up that mountain.
Next up, we have polynomials. A polynomial is a function that is essentially a sum of powers. A really famous example is the degree 2 polynomial. P of x equals ax squared plus bx plus c. We call it a quadratic function. No matter what numbers you plug in for a, b, and c, the graph of this specific model will always, without fail, be a parabola. You know, that classic U-shape.
Now, the physical shape of that parabola is entirely dictated by its leading coefficient. That's the a attached to the squared term. If that leading coefficient is positive, the parabola opens upward, kind of like a smile. But if it's negative, it opens downward, like a frown. Why does this actually matter? Well, if we're modeling the height of a falling ball over time, like the empirical model from Stewart's text, gravity is pulling it down, right? That means we use a quadratic function with a negative leading coefficient to perfectly map out that downward arc as the ball plummets to the ground.
Okay, let's head into section 3, power v's exponential functions.
Now, I need you to pay super close attention here because a massive number of students fall into a trap on this exact topic. Look at these two functions side by side. On the left, we have f of x equals x squared. On the right, g of x equals 2 to the power of x. Visually, as short little equations, they look incredibly similar. They both use a 2 and an x, but they behave wildly, completely differently. The one on the left, x squared, is a power function. Its base is the variable x, but its power is a constant 2. The one on the right, 2 to the power of x, is an exponential function. Its base is locked in as a constant 2, but the exponent itself is the variable.
So, the crucial point is this one simple question. Whenever you look at a function with an exponent in calculus, you must always stop and ask yourself, is the variable in the base, or is the variable in the exponent? Mixing these up is honestly one of the most major, catastrophic errors you can make, especially when we eventually get to derivatives. So lock this rule in your mind right now.
To show you why this distinction is so vital, let's look at what happens when x gets larger. If you plug the number 10 into the power function x squared, you get 100. Pretty simple. But if you plug 10 into the exponential function 2 to the power of x, you get 1024. As x grows, the exponential function absolutely explodes in growth compared to the power function. The exponential curve shoots straight up like a rocket, leaving the power function totally in the dust. That explosive growth is exactly why it's the go-to model for things like unchecked population growth.
Let's move on to section 4, trigonometric and transcendental.
Let's take out our specialty tools now. For anything in the physical world that constantly repeats, we use trigonometric functions. Think of the sine and cosine waves weaving across a graph. They're periodic, which means they repeat their values in perfectly regular intervals, and this brilliantly illustrates how math captures repetitive physical phenomena. If you want to model the rising and falling of ocean tides, the vibrating of a guitar string, or the rhythmic pulsing of sound waves, these trigonometric functions are the exact tools you need. In Stewart's catalog, trigonometric functions, along with exponential and logarithmic functions, are grouped into a category called transcendental functions. Now, I know it sounds like a big, intimidating word, but it just means functions that are not algebraic. They transcend, or go beyond, simple algebra. You literally can't construct them just by adding, subtracting, multiplying, or taking roots of polynomials. They're basically in a class of their own.
All right, section 5. Let's move to our challenge and see how this all builds together.
It's time for a little final exam to gamify what we've learned today and drive some active recall. Look at these 3 distinct graph shapes. Graph A is a straight line going downward. Graph B is a parabola opening downwards, kind of like a frown. And graph C is a curve starting low and then exploding upward. Now we've got 3 equations presented in random order. Equation 1 is y equals 3 to the power of x. Equation 2 is y equals 5 minus 2x. Equation 3 is y equals negative x squared plus 4x. I want you to synthesize everything we literally just talked about regarding slopes, leading coefficients, and the explosive growth of variables in the exponent.
Here is your challenge for today. Can you match each equation to its correct graph? I want to see who gets the full toolbox right. Go ahead and write your answers as a combination of the letters and numbers like A1, B2, C3, right down in the comments below. Take a minute to really think about why each equation matches its visual shape based on the rules we established today. That is it for this explainer. Keep practicing with these tools, and I will see you all in the next explainer where we're going to learn how to build new functions from old.